All right, guys, for today's lesson, we're going to be looking at the composition of functions. Before we begin, our warm-up says that Sarah Sung is shopping and finds several items that are on sale at 25% off the original price. The items that she wishes to buy are a sweater, originally at $43.98, a pair of jeans for $38.59, and a blouse for $31.99. She has $100 that her grandmother gave her for her birthday. If the sales tax in San Mateo, California, where she lives, is 8.25%, does Sarah have enough money for all three items? Justify your response. So, of course, for this example, what we're going to be doing is first figuring out what the pre-tax or subtotal of her purchase is, and that would include adding up the prices for all of these. So, the first thing we need to know is, well, what is $43.98 plus 38.59 plus 31.99? And that gives me $100.14 and 56. Well, if I stop there, clearly she doesn't have enough money because she only has $100. But I go back and look, and I remember it saying that those items are on sale for 25%. So what I need to do now is figure out what the sales price would actually be. And there's two ways of looking at this. I don't like the feature, but it doesn't do a dot really good. Okay, sales price would be. Now there's two ways of doing that. One of those is that, of course, we could simply multiply 0.25 times each one of those, and that would be how much you're going to take off. And then you'd have to subtract it. The quicker way, though, would be, if it's 25% off, that means you're only paying for 75% of the original cost. So the quickest way would simply be to take the 114.56 and multiply that by 0.75, which means that the items on sale would now give us a subtotal of $85.92. Okay, well that sounds perfect. She's got $100. I think she can afford it. Oh wait, we're forgetting that she also has to pay sales tax. And right now, where she lives, there's an 8.25% sales tax. So we need to figure out how much that is going to be. Now, again, there's two ways of doing that. You could simply multiply the 8.25% times 85.95, but then add that amount to the original $85. Or you could say that since this is an additional percentage, she's already paying 100% of the $85.92. So we could say 100%, so 1.0825, and times that by 85.92, and that would give us exactly how much she is going to owe. And that amount would be $93, and if I round to the nearest cent, 1 penny. So sure enough, she does have enough money because she only has $100, and she only has to pay $93.01. And so the justification would be that she does have enough money. All right. All right, so before we get into the composition of functions, it's very important that we take a minute and we talk about the operations on functions. Now, since elementary school, you've been taught about the 4 basic operations of arithmetic. Those include addition, subtraction, multiplication, and division. And since we've learned from algebra that variables and such are just an extension of the real number system, then we can actually add, subtract, multiply, and divide functions as well. So let's say that you have two functions, namely f of x and g of x. If they both exist, then you can calculate or find the sum, difference, product, and quotient of those two functions below. So for example, if I want to know what the sum of the two functions f and g are, you can simply add those two functions together. If I wanted to find the difference between those two functions, I could simply subtract those two functions. Also, if I wanted to find the product, I would simply multiply them together. And finally, if I wanted to find their quotient, I would simply set up a ratio or fraction. Now, the most important thing is that this last one, that g of x cannot be, that function cannot be equal to 0. Because remember, we can't divide by 0. That's undefined. So, I mean, basically, at the very simple as it can be, if I said that one function was 6 and another function was 2, if I were to ask you what f plus g would be, that would simply be f of x plus g of x, or just simply 8. If I wanted to know what the difference of those two functions are, it will be f of x minus g of x, and so that would be 4. If I wanted to find the product of those two functions, it will be f of x times g of x, so that would be 12. And then if I wanted to find the quotient of those two functions, then that would simply be 6 divided by 2, or 3. So the same operations that we do with our number system can be applied, generalizations, to algebraic functions. So let's take a look at a concrete example. So for example 1, it says, if possible, use each representation of f and g to evaluate these four expressions: f plus g of 4, f minus g of negative 2, f times g of 1, and f divided by g at 0. Now notice we have three different representations here. We have a graphical representation, we have a numeric representation, and we have a symbolic or algebraic representation. They all represent the same function, so we should get the same answer for all of them. All right, so let's start off with f plus g of 4, which we know that that means to simply find f of 4 plus g of 4. Well, let's first look at it with the graphical representation. Keep in mind that f of x is the graph of the line, and g of x is the graph of this radical function. So f at 4. At 4, where's the value of f? 1, 2, 3, 4, 5, 6, 7, 8, 9. On the function g, where's the value of 4? 1, 2. So that should give me an answer of 11. If we look at it through the numerical representation, f of 4 is 9, g of 4 is 2, 9 plus 2 is 11. And finally, if we look at it from the symbolic representation, if you simply plug in 4 into the function, you would get 8 plus 1 is 9. If you plug 4 into the g function, you would get the square root of 4, which is 2. 9 plus 2 is 11. So sure enough, they all check out. All right, if we do f minus g of negative 2, that's the same thing as f of negative 2 minus g of negative 2. Well, let's look at it from the graphical representation first. F of negative 2 is at 1, 2, negative 3. G at negative 2, well, wait. The g function doesn't go to negative 2. Negative 2 is not a part of the domain of the g function. So that does not exist. So in other words, I can't calculate it. Well, let's see if we can confirm that numerically. The f function at -2 is -3. The g function at -2, wait, has a line there. There's no value here. So I can't calculate it. Huh. Well, what about the symbolic way? Well, f of -2 would still, again, be 2 times -2 is -4, plus 1 will be -3. But then when we plug in -2 into the other function, you realize what the problem is. We can't take the square root of a -2. So that is why it does not exist there, and that's why it's not a part of the domain. So for this example, we simply have an answer of does not exist. All right, for f of g of 1, that simply means f of 1 times g of 1. And so let's look at it from the graphic standpoint. F at 1 is at 1, 2, 3. G of 1 is at 1. So 3 times 1 is 3. We should be able to confirm that numerically. F of 1 is 3. G of 1 is 1. 3 times 1 is 3. And then from a symbolic standpoint, f of 1 would be 2 times 1 is 2, plus 1 will be 3. G of 1 would be the square root of 1, which is 1. 3 times 1 is 3. And then finally, for the last one, f divided by g of 0 would simply be f of 0 divided by g of 0. So let's look at it from a graphical standpoint. F at 0 is at 1. G of 0 is at 0. Oh, wait, that does not exist because 1 divided by 0 does not exist. Let's look at it from a numerical standpoint. F of 0 is given, it's 1. G of 0 is given, it's 0. But just because we got numbers, again, you can't divide by 0. And so, again, even if you did it symbolically, you still get 1 over 0, and it does not exist because you cannot divide by 0. All right, for example 2, it says let f of x be equal to 2 plus the square root of x minus 1, and g of x equals to x squared minus 4. So we have a radical function for f of x, and we have a quadratic function for g of x. I know that f of x is a radical function because it has the square root. I know that g of x is a quadratic function because it's x squared. All right, so for part A, or for this problem, it says evaluate f plus g of 5. That simply means f of 5 plus g of 5. All right, well, f of 5 would be 5 minus 1 is 4, square root of 4 is 2, 2 plus 2 is 4. G of 5 would be 25 minus 4, that would be 21, so that should give me an answer of 25. All right, for f minus g of 1, so that would be f of 1 minus g of 1. F of 1, 1 minus 1 is 0, the square root of 0 is 0, 0 plus 2 is 2. G of 1, 1 squared is 1, 1 minus 4 is -3, so you get 2 minus -3, so that would be 5. All right, for f of g of 0, we'd have f of 0 times g of 0, but we have an issue. F of 0, if you plug in 0, you'd get 2 plus the square root of -1, which is not a real calculation. So that would simply end up being does not exist. And then f over g of 3 would be f of 3 divided by g of 3. So f of 3 would be 3 minus 1 is 2. There's no perfect square root of 2, so we can just leave it alone. So 2 plus the square root of 2 over, and then g of 3, 3 squared is 9, 9 minus 4 is 5. So I'd get 2 plus the square root of 2 over 5. All right, so now let's talk about some more notes. And now we're going to talk about the composition of functions. Now, function composition is very important because what happens is, think about a practical example. If you think about cotton, cotton is used to produce or manufactured into cloth, and then the cloth is taken and it's used in manufacturing to make clothes. So you could argue that, yes, clothes are a function of cloth. So let's say that you had X, Y, and Z. So you could argue that clothes is a function of cloth. So Z of Y is what I want to write. Z of Y. In other words, you input cloth, you output clothes. Okay? But then you could argue that cloth is a function of cotton. So cloth is a function of cotton. So then if there's a relationship between clothes and cloth, and there's a relationship between cloth and cotton, wouldn't it stand to reason then that clothes have to be a function of cotton as well? So in other words, since cloth is a function of cotton and clothes are a function of cloth, then wouldn't that stand to reason that you'd have a function inside of another function? And that's the idea of function composition. Composing functions. Now, the symbol that we use to represent function composition is basically a little circle, and it's read G of F, and that represents the function F inside of the function G. And that's the symbology for function composition. So, for example 3, it says, let f of x equal x squared plus 3x plus 2, which, again, that is a quadratic function because of it being x squared. And let g of x equal 1 over x. That's a rational function because it's a fraction. It says, for part A, evaluate f of g of 2 and g of f of 2. So, for part A, f of g of 2, that means I want to know what you get when you have 2 inside of the g function and then take that answer and plug it inside of the f function. So I guess it would be important for us to first figure out, well, what is g of 2? Well, the g function is 1 over x. So if you plug in 2, you get 1/2. And so now that you have that answer, what you do is you take that answer and plug it into the other function. Always start on the inside and work your way out. So then we'd have 1/2 squared, which would be 1 to the 4th, not 1 to the 4th, 1/4, plus 3 times a half would be 3/2, plus 2. And yes, it's important that you know how to add these fractions. Common denominator, so 1/4 plus 6/4 plus 8/4. Add all that together, you get 15 over 4. So that is f of g of 2. Now, how do you think that compares to g of f of 2? Do you think these are going to be the same answers? Well, this time I want to know what f of 2 is first, then take that answer and plug it into g. So, let's figure out what f of 2 is. So, f of 2, you plug it into here. 2 squared is 4. 2 times 3 is 6. 4 plus 6 is 12. Sorry, 4 plus 6 is 10. 10 plus 2 is 12. So, I get 12. And then take that answer and plug it into the g function. That gives me 1/12. So, notice that I do not get the same answer. Do not get the same answer. So then that would be, let's see, 4 plus 6, 10 plus, yep, okay. All right. So that was exact concrete answers. Well, for part B, it says find the composite functions defined by f of g and g of x. Are they equivalent? Well, if we just showed that at a specific value they're not equivalent, then clearly they're not going to be equivalent anyway. So, for part B, let's just go and find what the f of g of x function would look like. Again, that means I want to plug the g function into f. So that would simply be 1 over x squared plus 3 times 1 over x plus 2. So you see all I did was just simply plug in 1 over x into each one of my x's. And then for g of f of x, I would plug the f function into g. Well, that's even easier. I'd simply have 1 over x squared plus 3x plus 2. And so that would be my two functions. And then for part C, it says find the domains of f of g of x and g of f of x. So the domain, remember, when we're talking about domain, you look for restrictions. Restrictions can include radicals, where we don't want to have a negative radical, negative number underneath the radical, which is not the case for either one of these. Or with fractions, you don't want the situation where the denominator is equal to 0. Well, so for f of g of x, I notice I have 1 over x. This means that I do not want x to be equal to 0, because that would give me an undefined answer. So I do not want x to be a part of my domain. So the way I'd write that with interval notation would be from negative infinity to 0, not including 0, and then from 0 to infinity. And then for g of f of x, this one is another issue, right? We don't want, let me put it in blue, we don't want what's in the denominator, which is this quadratic. We don't want that to equal to 0. And so this does have two solutions that we would not want to occur. If you factor this, remember from factoring from algebra, this factors into x plus 2 times x plus 1, which gives us the two values we do not want to happen, which are negative 2, and we don't want negative 1, because that would cause that expression to be 0 in the denominator, and you can test those out. So we don't want those two values, so the domain for the second one would be from negative infinity to negative 2, then from negative 2 to negative 1, and then from negative 1 to infinity. And that would be my domain. All right, for example 4, it says find f of g of x and g of f of x for each one of these. So this is really 4 problems in one. So for f of g of x, if you want to practice it, that means the g function is inside of the f function, so that would be the square root of 2 times 1 over x plus 1, so that wasn't too bad. And then g of f means plug the f function into g, so that would be 1 over the square root of 2x plus 1. So that wasn't bad either. All right, for part B, f of g of x, so take the g function, plug it into f, so that would be 2 times x squared plus 5, don't forget the minus 3. And then g of f of x will be the f function, so that would be quantity squared 2x minus 3 squared plus 5. Okay? All right. For example 5, it says use the graphs of f and g shown in the graph below, evaluate the expression. So let's look at part A first. So it wants f of g of 2, so that means f of g of 2. Well, the first thing you know is I need to find out what g of 2 is. Notice that the f function is the linear function, and then g is the quadratic. So what is g of 2? Well, at 2, g is 1, so I'll have f of 1. And then at 1, f is 3, so my answer would be 3. All right, what about g of f of negative 3? Well, let's figure out what f of negative 3 is first. So at negative 3, f is at negative 1, and then at negative 1, g is at negative 2. And then finally, what about f of negative 3? Let's first figure out what f of negative 3 is. At negative 3, f is at negative 1, and then at negative 1, f is at 1. And so that will be my answer for that one. All right. The last example is an application-based problem. And again, to try to put this into perspective and what we notice. For example 6, it says depletion of the ozone layer can cause an increase in the amount of UV radiation reaching the surface of the Earth. We know that. So we know there's a relationship between our ozone layer and the amount of UV radiation that enters the Earth's surface. As the ozone layer decreases, more UV radiation comes in. So if you can imagine that if you're talking about the ozone layer and you're talking about UV radiation, as the ozone layer as the ozone layer decreases in value, the UV radiation is going up. So UV radiation is going up. So it's like that. That's a good way of saying it. So as the ozone layer is getting as the ozone layer is getting more protected, then the UV level is going down. But there is a relationship there. Okay. All right. So that's one relationship. An increase in UV radiation is associated with skin cancer. We know that the more UV radiation that you get, the more likely a chance of you getting skin cancer is also. So now we have that the percent in UV radiation is related to skin cancer. So the more UV radiation you're exposed to, the higher chances increase in skin cancer. So you have two distinct relationships, but they're related to each other. So what I'm saying is that if there's a relationship between the ozone layer and UV radiation, and there's a relationship between UV radiation and the percent of skin cancer, then there has to be a relationship between the level of the ozone layer and skin cancer. And that is, again, what function composition is. It says in the table below, the function f computes the approximate percent increase in UV radiation resulting from an X% decrease in the thickness of the ozone layer. The function g, shown in the table below, computes the expected percent increase in cases of skin cancer resulting from an X% increase in UV radiation. For part A, it says find g of f of 2 and interpret this calculation. Well, g of f of 2, the first thing we got to figure out is, well, what's f of 2? Well, f at 2 is 3.0. And now, what's g of 3.0? That's 10.5. Now, again, this is important, guys, in math, especially as you go into college. So what? I got an answer. But if you're not able to justify and tell me what that answer means, it doesn't mean anything. Okay? So what does that answer mean? Go back and look at the function, f of 2. So the percent increase in UV radiation. So that means if there is a 2% decrease in the ozone layer, there's going to be a 3% increase in UV radiation. And then if there's a 3% increase in UV radiation, that means there's going to be a 10.5% increase in skin cancer. So again, it's very important that you're able to justify and interpret what the math is that you're doing. So again, let me reiterate that. What you found was that given a 2% decrease in the ozone layer, there is a 10.5% increase in skin cancer. And so in between there, we know that the 2% decrease in the ozone layer causes a 3% increase in UV radiation, which in turn causes a 10.5% increase in skin cancer. So A leads to B, B leads to C, A affects C. Okay? So just keep that in mind. For part B, it says create a table for G of F and then describe what it computes. Well, if you do G of F, again, that just plays on part A. G of F would compute the percent increase in skin cancer given the percent decrease in the ozone layer. So if you were to create a table, it would simply be, your G of F table would be like F, and then it would be G of F of X. That would simply be like if there's no percent decrease in the ozone layer, then there is no % increase in skin cancer. If there's a 1% decrease in the ozone layer, that leads to a 5.25% increase in skin cancer. And you can go on and see how, as you would go up in these numbers, it would simply be the range of this last one would go all right there. All right, that's it for today's lesson.